Okay, so where are we? Oh, we're not here. This was a discussion of the homework. But we are here. So let me remind you what we did. Oh, maybe before, let me tell you what we will do. So I want to go a little bit on our side, totally unrelated to knot theory, and tell you how this stuff is related somehow to the four-color theorem. And I started saying it last time, and I want to say it in a little more detail. And then I will tell you a little bit about expansions, which is towards the proof of the fundamental theorem. So, but anyway, let me remind you what we did. So, we computed W of GLN. In fact, to be fair, it was the W of GLN in the n-dimensional representation on a diagram like this, and the computation was very easy. Every place you saw an edge, you replace it with a two-lane highway. Every time you saw an intersection, a vertex, you replaced it by a difference of the two ways of two different kind of interchanges, if you wish. And the black just became single edges. So basically, if you do it to a Y diagram, you get this minus that, and then every loop is a chain of equalities of variables that are summed from 1 to n. So basically, every loop gets assigned a single number from 1 to n. So if you have 3 loops, the total sum will end up being n cubed. If you have, like in this picture, only 1 loop, the total sum will be n. So this diagram gets evaluated to n cubed minus n. And, well, this is way simpler than the definition. The definition becomes something very simple. But let me say that this is actually still, if you have a diagram with a large number of internal vertices, this is still exponential time. Okay. So, in homework 6, question 2, I've asked you to prove that if a diagram D is blue, so what I mean by blue is that it has no black line. So all the lines are internal. All the lines are like chords and not skeleton line. So, you know, here is a blue diagram. Here's another one. Here's another one, right? So if a diagram is blue, then its evaluation in GLN is a polynomial of degree, what was it, v over 2 plus 2 or something, where v is the number of vertices. So it's a polynomial, and if you look at the coefficient, the top degree coefficient, so WGLN up top, namely the coefficient of the highest degree that could occur, which is again v over 2 plus 2, then this coefficient up to a sign, so in absolute value, is equal to the number of planar embeddings of that diagram. Okay? So that's the homework. And then let me also review the last 1 minute of hour 19, so the previous hour, we're now in hour 20. So if D is a blue diagram and it is also planar, then its evaluation in SL2 is the number of edge 3 colorings of D, up to a sign. So briefly, why was this true? So this was true because SL2 is really isomorphic to, so SL2 is isomorphic to SO3. The SO3 is generated by 3 infinitesimal rotations. So the rotation about the x-axis, the y-axis, and the z-axis. The commutation relations of these 3 generators, so if you write x1 and x2 and x3, if these are the generators, then their commutation relations are that xi, sorry, it's uppercase x, not lowercase x. So xi commutator with xj is xk provided xk is the third. So a different way to say it is to say that it's epsilon ijk xk, and in fact summation over k, where epsilon is the totally antisymmetric tensor. So if ijk is a permutation, then it's the sign of that permutation, and otherwise it's 0. Okay? And this implies that, so I didn't even bother to compute the tensor TAB, and the reason is that it really doesn't, so okay, TAB is proportional, it's not equal, it's proportional to delta AB. I think it's twice delta AB or something. Sorry, T lowercase ab is twice delta AB, and T uppercase AB is half delta AB. Okay? But it really doesn't matter. So I lied to you. This is here not equal to the number of edge 3 coloring. It's only proportional to the number of edge 3 colorings. But the point is that the constant of if you multiply T by 7, T appears once for each edge. So you end up multiplying the weight, the overall weight of the diagram by 7 to the power the number of edges, which is a fixed number. Okay, so so I really don't care about figuring out exactly what this coefficient is. You know, maybe I should have just figured it out, and then it would have been simpler. I could just say what it is instead of telling you why I don't care. Anyway, okay, so anyway, if you have a diagram, then the number of, then the weight associated with it is the number of ways of coloring its edges with the colors 1, 2, and 3, such that at every vertex all 3 colors appear. And then you take such a coloring with a weight which is the sign of the permutation of colors that you see around it. So for example, for this one, you see 1, 2, 3, so it's plus, 1, 2, 3, that's plus, 1, 2, 3, that's also plus, 1, 2, 3, that's, so all of the weights here are plus, so this coloring contributes 1. Okay? The claim is that for a planar diagram, all colorings have the same weight. Sorry, not the same weight, the same, yeah, the same sign. And I'm not going to show it.
A question.
Yeah.
So if you talk about coloring, are you coloring the edges or the points?
I'm coloring the edges.
Okay.
With the colors 1, 2, 3. So I'm not going to show it. It's not hard. Okay, but this is an aside. I actually only want to give you the flavor. So it's a relatively easy statement. So yeah, so that's how we get this conclusion, that it's the number of edge 3 colorings, or proportional to the number of edge 3 colorings. And then I need to tell you a little bit of a cute statement from combinatorics, and I do want to show it because it is cute. This one is just not interesting. So the statement is that if D is planar, then the number of edge 3 colorings of D is equal to the number of face 4 colorings of D, and I'm lying a little bit. I think there is a factor of 4 here, and when I say face 4 colorings, I mean the same thing that appears in the 4-color theorem. So, you know, if you have a planar diagram, it defines a map, and then you can ask yourself, can you color the countries, namely the faces, with 4 colors such that, or how many ways can you color the countries so that no adjacent colors have the same color, no adjacent countries have the same color. So like here, one such coloring will be 1, 2, 3, and then the face at infinity is forced to be colored 4. Okay? So, why is this true? So this is kind of lovely. So this is true because for the 4 colorings, use the colors, right? You know, it actually matters which color you use for the proof. You know, if you think all colors are the same, you're wrong. You have to choose the colors right. So the colors you use are the colors in the group Z mod 2 cross Z mod 2. So these are the colors 0, 0, 0, 1, 1, 0, and 1, 1, and they form a group. You can add colors by the rules of the group Z mod 2 cross Z mod 2. So this is for the face colors. And in fact, when you want to use the edge colors, so when the 3 colors you would use for edge colors, so use the edge colors, so all the elements of this group minus the identity. So Z2 cross Z2 minus the identity color, so minus 0, 0. In other words, use the colors 0, 1, 1, 0, and 1, 1. And then, if you have a face 4 colorings, so if you have a face 4 coloring, so for example, let's take the same map and color it with the colors 0, 0, 0, 1, 1, 0, and 1, 1. Then you can map it to an edge 3 coloring by mapping every edge to the difference of the 2 faces next to it. Okay, so you map, so every edge becomes the difference of the 2 faces next to it, and when I say difference, since the group is 2 torsion, I could say sum just as well, and equally well I could say it doesn't matter if I take the difference this minus that or that minus that, it's the same difference. Okay, so if I do that, the difference between these two is 0, 0, sorry, 0, 1. the difference between these two is 1, 0. The difference between these two is 1, 1. The difference between these two is 0, 1. The difference between 0, 1 and 1, 1, the infinity one, is 1, 0. And the difference between 0, 0 and 1, 1 is 1, 1. Now, since the four-coloring was a legal map coloring, so no two faces, no two adjacent faces had the same color, it means that the edges are never 0. So you get coloring in the legal colors for the edges, right? Also, so whenever you have a vertex, so if you have a vertex, then in the vertex, three faces are all adjacent to each other. So the three faces must have different colors. So in particular, so whatever color this face has, this one has a different color, and this one has a color which is different than that one. So these two differences are not the same. So the two edges end up being colored with different colors. So, but that was true for any pair of edges. So these two are colored with different colors, and these two are colored with different colors, and these two are colored. So basically, all three edges are colored with different colors, so you get a legitimate edge 3 coloring. So I've just defined a map. So this just defines a map from face 4 colorings to edge 3 colorings. Now I want to construct an inverse map. Well, and it shouldn't be quite an inverse map, because I said that that 4 times the number of edge colorings is the number of face colorings. So in fact, the map here is 4 to 1. Okay? But I still have a rough inverse map. So what is the inverse map? So suppose you have a diagram with an edge 3 coloring. So let's take, you know, I'm not going to be creative, I'll just copy the edge coloring from here. So 0, 1, 1, 0, 1, 1, 1, 0, 1, 1, and 0, 1. So how do I color the faces so that the differences will be as written on the edges? Well, the first face I choose arbitrarily. So the face at infinity I color randomly. There are 4 possibilities. So the face at infinity I will color, let's say, 0, 0. Okay? But anything that I start with will work. And that forces how I would color the other faces, because when I cross into this face, I must add 1, 0. Right? So this has to be colored 1, 0. When I cross into here, I must add 1, 1. So this must be colored 1, 1. When I cross into here, I must add 0, 1. So this must be colored 0, 1. So this forces the coloring of the faces. Now you have to check. Okay, sorry. Why are adjacent faces given different colors, because when we cross an edge, we add the color of that edge. And the colors of the edges are not zero. We've removed zero. I mean, we're using only the 3 colors that are not zero. So we always add something. But the next thing you have to check is you have to check that if you make a path in the graph, so, you know, if I start from 0, 0, and I cross into here, then I cross into here, then I cross, then I come back to 0, 0, I have to check that the colors that I will get along the path are consistent. Right? I have to check that, which amounts to saying, you know, saying that, so basically I have to check that every time I go around such a loop and add all the edge colors, so really it's happening here. Every time I go through a loop and add the edge colors that I see along the way, I must end up adding 0. The total sum must be 0. Because otherwise I will have an ambiguity. Otherwise it means that if I wanted to go from here to here in 2 different ways, I would get different sums, which means that I'd have an ambiguity for how to color this face. So to show that the map is well defined, namely that there is no ambiguity going from infinity to any other face, I mean that if you go in 2 different ways from infinity to another face, you get the same answer, is the same as showing that closed loops add to 0. And why do closed loop add to 0? Well, every closed loop you can slowly contract. And every time you contract it, you make it pass, you make it a bit shorter, things change when it crosses, when you contract it, it crosses a vertex. So really all I have to check is that every time I go around a vertex, really all I have to check is that every time I go around a vertex, the sum of the colors around it is 0. But that's a property of the group Z2 plus Z2. Namely, the sum of the 3 non-zero elements, 0, 1, 1, 0, and 1, 1 is equal to 0. QED. I hope you followed. Sorry, I tried to give it, I don't know, I hope you followed. Oh. And this map is of course 4 to 1 because I had a free choice at infinity. Or one free choice. I mean, I could have started anywhere. Right, and okay, good. So, what does it mean? So, so now let's go back to the 4-color theorem. The 4-color theorem is equivalent. I mean, I'm just rephrasing it. The 4-color theorem says every planar map has a coloring in 4 colors. Okay? So a different way to say it is to say that if you have a diagram D, if the number of planar embeddings of the diagram D is not equal to 0, meaning it is a planar diagram, then the number of face 4 colorings of D is not equal to 0. This is clearly equivalent to the 4-color theorem, right? But This is equivalent to saying, so by your homework assignment, this is equivalent to, oh, sorry. So, yeah, there is some well-known thing in logic, right? If A implies B, then that's equivalent to B, so to not B implies not A, right? So this is equivalent to if the number of phase 4 colorings is equal to 0, but that's the same as saying that WSL2 of D is equal to 0, then this implies the negation of this. So WGLN top of D is equal to 0. So here you go. This statement about Lie algebras and diagrams is equivalent to the 4-color theorem. Now, so now I have to say something about Lie algebras that people may or may not know. So if you took a course on Lie algebra, on Lie algebras, on representation theory, you sort of know that SL2 is the mother of all Lie algebras. I'm not sure how to say it. That every other Lie algebra is somehow an amalgamation of SL2s. So if you look, for example, at GLN, so really, or roughly speaking, every Lie algebra is just sort of a flower with petals SL2, but they share a common union, a common center. Or more precisely, every matrix algebra is or GLN in particular, is a union of lots and lots of SL2s which share a common, which share the diagonal. So basically, if you look at GLN and you restrict your attention to the entry here, the entry precisely opposite to it, and the entries on the diagonal corresponding to it, you get a copy of SL2. So GLN is somehow an amalgamation of many copies of SL2, which somehow all share the diagonal. I'm being imprecise. If you go to, if you take a class on Lie algebras, it becomes precise. And it becomes important because the study of Lie algebras goes through the study of SL2. You first fully understand SL2, then you fully understand all other Lie algebras. So if you have this perspective, then this thing sounds like a completely natural statement. If a diagram is degenerate for is trivial from the perspective of SL2, is invisible for SL2, then it's degenerate for SLN. Which sort of makes sense because SLN is just a bunch of SL2 held together. Okay? So this sounds like a statement. So from the perspective of people who know Lie algebra, this sounds a reasonable statement. Sounds like a reasonable statement. But unfortunately it isn't. So it just sounds like a reasonable statement. But when you actually try to prove it, nothing good comes out of it. You're stuck with proving the 4-color theorem back again. So so it's fun. I don't know. I'll put a smiley here to say that it's fun, but it's actually, other than fun, it's not particularly useful. Okay. Any questions, comments? Leonard, it seems like you were speaking, but your sound was off. What?
Planar.
Sorry?
I was asking about the planar embeddings. What do you mean by planar embeddings?
Ways of putting the diagram in the plane.
Oh, okay.
So, for example, or ways of putting, yes, so for example, consider I don't know, this graph. Okay, so this graph can be embedded in the plane in 4 different ways, because you can flip this side or you can flip that side. Oh, that flipping that. So yeah, so I suppose I have to give names to the vertices 1, 2, 3, 4, and then flipping this side is a distinct embedding than not flipping it. Okay?
Do you define a planar embedding as 1 into S2 then?
Yeah, into S2, yes. Sorry, the plane is S2. Okay, so, yeah. Okay, so I wanted to make another comment also following a question by Leonard. So Leonard asked, does the framing independence relation hold for weight systems coming from Lie algebras? So when I wrote W, G, and R, so the weight system coming from a Lie algebra and a representation thereof, well, it satisfied STU and IHX and antisymmetry, therefore it satisfied 4T, therefore it's a linear functional from A into Q, but, okay, therefore by the fundamental theorem for framed knots, it corresponds to an invariant of framed knots. But what if I wanted an invariant of unframed knots? So that was precisely the point of homework 6, question 1. So homework 6, question 2 was what we talked about before. But homework 6, question 1 constructed a map from AR into A. I think it was called P. And it's a super well-behaved map. I mean, maybe it's complicated to define, but it's very well behaved. It preserves all this. It's a morphism of Hopf algebras. Now, by the way, constructing a map going the other way is trivial because AR is a quotient of A. So you just project. But this map is hard. Okay? But now, suppose you choose a Lie algebra and a representation, it gives you a map from A into the ground field, and then if you compose the two, you get a map from AR into the ground field. Maybe I'll call it WG, R bar. Okay? And therefore you also get an invariant of unframed knots. Okay? Good. And, well, but all of this depends on the proof of the fundamental theorem, and we haven't yet proven it. And in fact, we will not prove it in this class. And the reason is that I want to give you a flavor of view of its proof. I don't want to go into the details of any of them. Okay? But all of them that I know, factor through the following proposition. So I want to start with the following proposition. Okay? So the proposition says that the fundamental theorem, meaning that every weight system satisfying 4T comes from an invariant. Okay? So in fact, the fundamental theorem for framed knots, and there is a similar formulation for unframed knots, is equivalent to the following statement. And in practice, you end up proving the other statement. So it is equivalent to the following statement. There exists an invariant of knots called Z, which is, so it's an invariant of knots, so it is defined on the space, on the set of all knots, and it takes value in the space A, the space of chord diagrams. You know, I think I told you that I tend to confuse A with its completion, with its graded completion. So it's actually defined in the completion, but very often, meaning in infinite series or some infinite sums of diagrams. But I will often drop the hat symbol with a property. So such that if you compute Z on a singular knot, so suppose K is M singular. Now, Z was defined on knots, but it has value in an abelian group. I mean, A hat, well, A hat is a Hopf algebra. It has lots of structure, but in particular, it's a vector space, therefore an abelian group. Therefore, every invariant of knots with values in A can be extended to singular knots. And the condition that I want is the following. So if you have an M singular knot, it has an underlying chord diagram. So it has an underlying chord diagram. So this is the chord diagram of D. But you see, I don't really want this to be equal to that. I want it to be equal to the chord diagram of D plus higher orders, higher degrees. Right? What?
Is this the chord diagram of K?
Yeah, the chord diagram, of course, of K, not of D. Thank you. Okay, so I want Z of a singular knot to be its own chord diagram plus terms of higher degree, meaning plus perhaps funny combinations of chord diagrams or linear combinations of chord diagrams, provided they're all of higher degree. Okay? So, okay, and in practice, the way the fundamental theorem is proven is you don't show that every weight system comes from an invariant, you just construct in bulk one single invariant that does it all. Okay? So, but why is this true? So, well, it's an if and only if statement. So, it has two sides. Suppose I had such an invariant Z. Okay? So, suppose such Z is given, and now I have to show that every weight system comes from an invariant. So, suppose W is some weight system. So it belongs to the degree M piece of A dual. Okay? Then I have a map from, you know what, rather than writing knots every time, let me declare that the space of all knots is called calligraphic K. Okay? So now I have a map going from K into A. This is the map Z. And I have a map W going from A into the ground field. So A is the direct product of all the AMs, so just extend W by 0 on all other degrees. So W is supported on degree m. Okay, so W is supported on degree m, and on degree m it's the W that was given. Okay, maybe I should give it a new name, W extended. Okay, but anyway, the composition of these two maps is a knot invariant with values in the rational numbers. So let's call this invariant V, and I claim that the weight system of V is W. I claim that V is what you wanted. So let's compute V evaluate, sorry, not V, right? I want to show that the weight system of V is W. So I want to compute the weight system of V on a chord diagram D. On a chord diagram D, right? But how do I compute the weight system of an invariant on a chord diagram? I find a knot whose underlying chord diagram is D. So I find K such that the diagram underlying K is the diagram I have given. So this is and then I evaluate and then I let this so again W sub V is like the mth derivative of V, so I basically differentiate V using this singular knot, right? So this is by definition equal to V, wrong color, equal to V evaluated on this K, sorry, on this K that I just found. But V is the composition of Z and W. So this is W evaluated on Z of K. But Z of K, by the condition defining Z, is the diagram of K plus higher degrees. Okay? So this is W evaluated on the diagram of K plus higher order terms. But the diagram of K is simply the diagram I started from. So this is W evaluated on D plus, but W was extended to 0 in all other degrees. So plus 0. And that's what we wanted. I wanted to show that the weight system of V is W, and I've just shown it. So this checks. Okay? And for the second direction, so now, sorry, I forgot which direction that was. That was going left, so now I have to go right. So for the second direction, so now suppose I know that every weight system comes from an invariant. Okay? So let A, M, I runs from 1 to dm be a basis of AM. So A, this infinite product of AMs is infinite dimensional. But each individual AM is finite dimensional. So I'm choosing a basis for each degree M piece, and it's the degree M piece is dm dimensional. So let this be the basis. Okay? Let WMI be the dual basis, which means that it's a basis of AM dual. But the fact that it's the dual basis means, right, what does the word dual basis means? It means that WMI evaluated on AMJ is the Kronecker delta function, delta ij. That's the meaning of the dual basis. And now define, oh, sorry. This WMI is a linear functional on A. And we have assumed that every linear functional becomes it comes from an invariant. So, by the fundamental theorem, so now I'm assuming the fundamental theorem, right? So, by the fundamental theorem, find V sub mi such that the weight system of Vmi is Wmi. And now I can assemble everything. So now, oops, okay. So now, define, so I want to define now this Z. So Z should go from nodes to A as follows. So if you are given a node K, I will define Z of K to be the sum over all M of the sum over I goes from 1 to di, so basically the sum over all m's and i's of the invariant Vmi evaluated on K multiplied by AMI. So first of all, this is a not invariant, so numerical not invariant, so it has values in Q. And this is just a diagram, an element, basis element of AM. So this whole sum here is an element of AM, and if I sum over all m's, I get an element in A. And okay, so I've given so I've defined a map from K to A. Now I have to check that it has the desired property. So suppose now that K is M singular, and let me compute Z of K. Well, Z of K is just that. Okay? So Z of K will be the sum as M goes from 0 to infinity of the sum over I goes from 1 to di of Vmi of K AMI. Now, in this sum, Vmi is of type M. Oh no, this is not the same M as that. Sorry, this M is a summation variable and this M is M singular. So you know what, let me call it M prime, the summation that appears here. Okay? But anyway, so if M prime is less than M, then since K is M singular and I'm evaluating a type M prime invariant on it, I get 0. So really, you can restrict your attention to summation starting from M. But you see, the degree for the statement of what I want the Z to satisfy, I don't care about degrees higher than M. So really, I can write the result as higher order terms that I don't care about, plus the term of exactly degree M. which is sum I goes from 1 to di of Vmi of k ami. But Vmi is a degree m invariant, and I'm evaluating it on an m singular knot, so the result is just its weight system evaluated on the diagram of that knot. So this is equal to, sorry, I'm running a tiny bit over time. This is higher order plus, which I don't care about, plus a sum over I of the weight system of Vmi evaluated on the diagram of k times ami. But the weight system of Vmi is really Wmi. And now I'm evaluating a dual basis on D and multiplying by the basis. That's the identity operation. So this is equal to the higher order terms plus dk, right? That's just the identity map. End of proof. And I'm sorry, I'm 2.5 minutes over time, but at least the theorem is done. So any questions or comments? So our goal next, and we will partially achieve it, because again I don't want to go into the complete details, will be to construct a once and for all invariant like that. One big invariant that has everything in it. And it's called the universal finite type invariant. Okay, so yeah.
So up to some quotient, I guess Z is an isomorphism?
Well, it's not an isomorphism. These are completely different spaces. These are knots, these are diagrams. Yes, you are right. There is a way to turn it into, yes, there is some completion of the space of knots that makes it an isomorphism. Okay. Well, so see you on, everybody left already, so see you on Wednesday. Bye.